One way that I used DOS back in the 1990s was to write Fortran programs. Now, I was a physics student at the time, and Fortran was the language of the day if you needed to write programs for data analysis or to run any kind of numerical simulation of a physics event. And we do actually provide a Fortran compiler in FreeDOS 1.3. It's on the bonus CD, which I have loaded here, and if I run fdimpls, you can see where I've installed it. So go down to Development, hit Tab to go over to the right-hand side, and then at the bottom of the list, you can see Watcom F is the name of the package. That's the Open Watcom Fortran compiler. It's a Fortran 77 compatible Fortran compiler. So let's write some Fortran. So the first thing we need to do is we need to set the environment. We can do that with the Open Watcom setenv bat file, and that's just right here in the devel watcom f directory. And so I'm going to type ow setenv, and that has set my environment for writing Fortran programs. Let's write something right here so I don't have to deal with any kind of paths and things like that. So let's go ahead and just edit a new program here called traj or trajectory.f. Now, if you haven't done Fortran before, it's very similar to BASIC if you've done BASIC programming. Couple limitations. Fortran's a very old computer programming language. It was originally developed using punched cards, and it has some obviously different syntax stuff from BASIC. But if you've done BASIC programming, this will look kind of familiar. Now, everything needs to be in uppercase for Fortran 77. Technically, some compilers will allow you to do lowercase, but as a longtime Fortran 77 programmer, I'm going to do everything in uppercase. One of the first things you need to note in Fortran programs is there's certain columns will mean certain things. For example, if I wanted to create a comment, you need to create put a C, for example, or a star in the first column, and that indicates the rest of this line is going to be ignored. It's a comment. And so this is a program to calculate a trajectory. I'm doing everything in uppercase because that's how I learned how to do it when I was learning Fortran back in the day. So I'm going to go over here to column 7. 1, 2, 3, 4, 5, 6. That's 6 spaces. Gets me in column 7. And that's where my program statements need to start. So a program needs to start with program. And you need to now label the program. So we'll call it traj. And then it needs to end with the term end. And so between there, I can now write my Fortran program. Now, there's different data types, and I'll leave it to you to explore different things you can do in terms of data types. But you can also have things like parameters, and I'm going to need the variable pi, and I could do like the very simple 3.141. I happen to remember the number for pi. It's 3.141, 5926553. 7, I think might be the next number, but we'll leave it at that. And then and we'll put another constant here, which is the acceleration to gravity. So grav equals, and that's 9.8 meters per second. I'm also going to need some variables, and so I'm going to go ahead and declare some variables. I could do an implicit thing, which is kind of sloppy Fortran programming, but let's just go ahead and say double precision. And I need some variables here. I need, since I'm calculating a trajectory, so it's basically like firing a cannon. I'm just going to track its progression over time. So I need to track its X and Y position over time, but I also need to track its X velocity and its Y velocity. And I'm just going to put a separate line here, double precision variable as well. It's the initial velocity, val 0, and the initial angle 0. And then do one more set of variables here. Double precision for the time that I'm going to be tracking and the time step. Now, if you're going to be doing some sort of a numerical simulation, which is what I'm going to be doing here, you'd probably be using a more robust method like the Runge-Kutta method or something. We're going to do a very simple, just calculating everything with standard equations of motion. Let's go ahead, by the way, start a little print statement. Print star that will tell the user what this program is about. So calculate a trajectory. Now we should do a thing here to print a prompt, and that is to enter the velocity and angle, and then I can now read star the velocity 0 and angle 0. Probably should do some error checking here, right? So let's do if. Now we can learn how to do an if statement, by the way, if we've done Fortran. And spaces, by the way, are pretty much ignored. So I can do a space, open paren. I can just do if paren with no space. But if the velocity 0 is less than 0, and you'd think that you'd be doing that, right? But no, actually, Fortran was originally done on punch cards, and there was no less than, greater than symbol, so we need to do .lt, means that is less than. So .lt dot means it is less than 0.0. Then we can print something. So we'll print a little message here. So we'll print back to the user velocity cannot be less than 0. And then we should probably jump back to do the prompt again, which we'll need with a line number, because that's how Fortran works. So we'll do a go to, we'll label it as 10. And then at the end of this if block, we can now do an end if. And up here where we had the velocity and angle, I'm going to do 10. And I probably should do one more quick error check here. If the angle 0 is less than 0, or same as you can't have less than, greater than, you also can't do like what we do in C, where it's like vertical bars. That doesn't exist in a punch card either. So you need to do .or to indicate it's an or statement, or angle 0 is greater than 180. Then we're going to do something here. That'll be the end if here at the bottom here. And then we need to say print angle must be greater than 0 and less than 180. And then go ahead and re-enter that. So go to 10. And I already have my end if. So there we go. All right, so we've done all that. That now has verified that we have entered in a value. And we'll do a print star of what that velocity 0 looks like. So vel 0 equals, and then vel 0, and then print star the angle 0 is, oops, that needs to be inside a quote. Angle 0 is angle 0. And now we can actually put that into an X component and a Y component for the velocity. And so the X velocity, remember we had that up at the top. Let's jump here to page up. There's our on our line down here, we had double precision of X and Y, but also the X velocity and Y velocity components. And so that's where we're getting that. So X velocity is going to be the initial velocity, velocity 0, times the cosine of the initial angle times pi divided by 180, right? So we always know that's the case, because to convert an angle into radians, well, there's 2 pi for every 360 degrees. That means there's 1 pi for 180 degrees, and so that's where we get our pi over 180, 180.0, by the way. I always like to put the 0. And why is this cosine? Well, if the angle is 0, think about it that way. If the angle is 0, then that means it's pointing horizontal from the ground. So it's all that velocity is going off to the one side. Nothing is going up. And the cosine of 0 is 1. So that is going to shoot us off to the right-hand side. So if you ever forget if it's cosine or sine, we're trying to convert components, that's how you do it. And then we'll do a y velocity is going to be velocity 0, oops, 0, times the sine of angle 0 times pi over 180. It's 180. And now we should probably print out what that looks like. So we'll do print star of x velocity and the y velocity. And let's just make sure that we're converting everything right. So before we go any further, let's go ahead and save what we've got. So we're going to do a file, and then, oops, I'll just do an exit here and save. And then we're going to do a Watcom. Instead of, we used to do, when we compile using Watcom C compiler, we do WCL. It's the Watcom C compiler and linker. But this is Fortran, so it's WFL, the Fortran compiler and linker on traj.f. And there we go. So I've got a little bit of time step as non-reference symbol, time, X and Y, and grav, because we haven't used those yet. And so we can ignore those. We've got our program here, so I can do traj. And let's say I had a velocity of, let's make it a nice test number here. We're just testing it. So a velocity of 100 at an angle of 0. And I should expect to see the x velocity component being 100 and the y velocity component being 0. So because this is 0 degrees at 100 meters per second. And so it read the velocity correctly, it read the angle correctly, and the x and y components are 100 and 0. So that's good. And so now if we do try and run that again, and this time it's a 100 velocity at 90 degrees. This should be pointed straight up. And that means that my x component velocity should be 0. My y velocity component should be 100. So we'll do that. And that is, the x component is minus 4 point something, but it's times 10 to the minus 6. So it's basically a little bit of math rounding here. So it's basically 0. And you can see the y component is basically 100. So that's good. That's good for this. So that we know that that part of the function is working well. So let's go back to our edit of our trajectory.f program and pick up where we left off. So now we've printed the x velocity and the y velocity. And let's go ahead and enter the time step. And so since I, like before, need to verify that we're doing some testing, so we should probably put a line number in there so we can go back to it. Print star, enter time step, and then read star time step. And then if the time step is less than 0, then we're going to let the user know, oops, you can't do that. Time cannot be less than 0. And then we're going to go to 20 so they can re-enter it. It's 20. And there's our end if. All right, now we can actually do the calculation. So let's start our initial values here. Our initial x position is going to be at 0.0, and our initial y location is going to be at 0.0. And we're going to start the time at 0.0. All right, and then as we print everything out, let's just do a little header here. The output, output is time. We're going to print the time. We'll print the x, we'll print the y, and we'll print the x velocity. Actually, why would I print the x velocity? There's no point in doing that. Let's just do the y velocity. Because x velocity should not change. So we'll do the y velocity. It's more interesting. And then that means we need to print that out. So print star, and then, this is going to be in quotes. So it'll be just the variables, time, x, y, and then y velocity. So that seems like that's the more interesting way to do it. And then we're going to do a kind of a loop here. And actually, if I'm doing a loop, we probably should put a number in here so we can jump back to this here. X equals, so let's remember our physics equations of motions. It's always X plus the X velocity times the time step, and Y equals the Y that we had before plus the Y velocity times the time step. Oops, time step. Now again, if we were going to be doing this in a more scientifically rigorous method, we use like Runge-Kutta method or something. But here I'm just doing a simple demonstration. So it's not just y plus the velocity times the delta in time. It's also when you subtract 1/2 at squared, right? That's the other part of it. So it's going to be 0.5. I'll just do the math ahead of time, right? 1/2 is 0.5 times grav. That's the parameter I have at the top. And then times time step squared, and I'll just do time step times time step. And then what is my y velocity? Well, x velocity is not going to change, right? So I could just say x vel equals x vel, but there's no point in doing that. So I'll say y vel equals the y velocity minus, and then what's our equation of motion in this one? It's the gravity times the delta in time, so time step. And now we can print this result in the time. So we're going to do a print star on time, and then x and y velocity. And then if y, the y location, is less than 0.0, that means it's hit the ground, then let's exit this loop. So we'll do go to 40, which we haven't written yet. And then otherwise, wow, actually I don't need to go to 40. I can actually say if y is greater than 0.0, then go to 30. And by the way, one thing we didn't also do is we didn't actually increment time, so we should probably do that here. Time equals time plus time step. All right, so then what that's doing is after it does all the calculations for what's the new x coordinate and what's the new y coordinate, and then what's the new y velocity and the new time, it then prints out the results. And as long as y is above 0, because it started at 0, as long as y is above 0, then keep doing the loop, right? So go back to line 30, which is calculating the new x and the new y, and so on and so forth. And then once we're done with that, let's just go ahead and just print a little message saying done. So print star done. And then we'll end the program, and I think that'll be it. So I think that should probably deal with what we're going to do. So let's go ahead and exit this. We'll go ahead and save it, and do the Watcom Fortran compiler and linker on traj.f. And do I see any errors? I do see a miss error. Yes, it looks like oh yeah, the word go to is actually GOT020, right? So thank goodness the DOS prompt has those little dots in the middle there. So we'll do edit our traj.f. And where's my go to? It's down here. Go to 20 right there. How is it I've never made that error in I don't know how many years? So there we go. There's go to 20. So it's an O instead of a 0. There we go. Exit. Yes. Watcom Fortran compiler and linker on traj.f. And I don't see any errors or warnings, which is good. And so let's do our trajectory program. This is what I would do all the time as a physics student. I would run sort of numerical simulations of things. Again, we're going to do, let's do 100 for our velocity and an angle of 0. That's pointing straight out. It'll hit the ground as soon as it comes out of the gun, and that's okay. And the time step will be, let's do 0.1. And then there it is. So it didn't take very long. It took the first step, in fact, before it actually hit the ground. So we know that worked out pretty well. And then let's do the trajectory again. We'll do 100 for our velocity and 90 degrees. That's pointed straight up. And our time step of 0.1. And there it goes. It's running a whole bunch of steps there. And after, looks like 20.5 seconds, it hits the ground. And at pretty much 0, because remember the second parameter there is the x coordinate, and that's minus 0.89, some other stuff, times 10 to the minus 5. So it's basically 0. And the y location was, of course, below the ground at minus 9. And it was going minus 100. So it that worked, right? So if what goes up will come down, and it'll come down at 0 at the same height. So that's good. In fact, the line are at the same speed. So at the line above it, you can see actually at 20.4 seconds, it had a height of 0.81. So it's right above the ground. And that was going at minus 99.92. So it was almost hitting the ground, and it was almost back to 100 meters per second, which is good. And so one more thing to do here, you can do trajectory on, let's do 100 meters per second. And at an angle of 45 degrees, and that's the best you can get in terms of range. And so let's see what our best range will be. And so our time step of 0.1. We can go 1,025 meters by shooting it at 45 degrees. Somewhere between 1,018 and 1,025, actually, because it looks like it was at 2 meters above the ground at 14.4 seconds, and it was almost 5 meters below the ground at 14.5. So somewhere between 1,018 and 1,025. So we'll call it 1,020. And so I would run these kinds of numerical simulations all the time. We would do things like take data in labs on a damped pendulum, something going under friction, and then we would go back and take notes in terms of what the angle and the locations were over different times. And we'd go back and we'd run numerical simulations to try and measure the dampening effects, or try to determine numerically the dampening effects, for example, of wind friction or other types of friction on our device. And so being able to write some sort of analysis program, and Fortran was the programming language of the day for science programming, was the way that we would do this. And once I had a Fortran compiler on my DOS machine, I didn't have to go down to our Unix lab all the time. And so just wanted to share with you writing some Fortran. So before I go, I wanted to thank everyone who supports me on Patreon. You really do make this channel happen. I say that all the time, but it always really is true. Some of you are supporting me at a higher level, and I want to thank you again here for that. So thank you especially for your support. Visit our website at freedos.org. Join us on Facebook, follow us on Twitter, and consider supporting me on Patreon. Thank you.